Hello, good afternoon to everyone. Is it audible?
Yes,
Can anyone respond? Can anyone respond to my voice?
yes, it's audible, sir.
Okay, thank you. Hello, good afternoon to everyone. Welcome to the webinar session, monthly webinar session on Code 5. And this is the fourth month webinar. And earlier we had done the webinar that to give the introduction to the Code 5. And webinar 2 is about the optical imaging fundamentals. And third webinar is about the uh, optical imaging fundamentals in second version. And fourth one is that to do in practical session on the code file, how to use that code file in user interface, and then how to use the expert tools to get the best performance. And I'm myself Medara Sreenivasulu. I'm working as a JRF under Dr. Vivek sir for the project of Startup Research Grant. The project name is the Design, Characterization and Fabrication of Micro Lens Array Imaging. As a part of the project, I'm going to start the session for using of Code5. That's the main focus on this webinar. Then coming to my webinar outline is that first introduction to Code5. It is just one bit presentation only. And Code5 applications, next user interface of Code5, and main focus is that design of the compact aspheric camera using tensor lens. Tensor lens is nothing bad, it's the basic version of camera, than which having the specifications that limited specifications. But with using of Code5 tools, we're going to improve the performance. That's we're going to discuss in detailed manner. First, Code5. Code5 is an optical design software. It is used by engineers to model, analyze, optimize, and provide fabrication support for the development of optical system for several applications. In this in this webinar session, we're going to experience all these four steps. First, model. Second, analyze. Third, optimization. And fourth, fabrication step. In fabrication step, we're going to use the tools like Aspire Expert and then Glass Expert and Tolerance Expert tools. We're going to use it. And with this webinar session, we're going to get the much awareness about the Code 5 in more effectively how to use the design in to get the more effective performance. And in Code 5 algorithms, they're going to use the more dominant technology to design the microlithographic lens that permit the imaging of the ultrafine lens on the computer chips. This is the best example for that, how precision we can get with the code file. Normally in our design, we're going to get the precision that it having after the decimal point, the digits will be the 9 digits. That much of precision we're going to get it. That's the best example. That's why I noted this point here. Next, my problem statement is that to design the compact aspheric camera using tensor lens. First, we're going to design the basic version of tensor lens, and then we're going to add the aspheric surfaces, and then after we're going to add the glass expert tool, and then we're going to compare all the results. And tensor lenses are the basic version of camera that it has the specifications that f number will be f/2.5 lens. That means it's a ratio of the focus point to and aperture diameter, and effective focal length is the 25 millimeter. Normally focal length is nothing but the distance between the center point of lens to the image surface when we have the one lens only. When you have the multiple lens, then we're going to calculate the distance that where the chief ray is going to touch the optical axis from that point to the last surface, that means image surface. That distance is known as effective focal length. And here we using the tensor lens having the number of elements as 4. 4 elements means each element have the two surfaces, and 4 into 2 total 8 number of surfaces we're going to observe it. And the field of view is that 25 degrees, and if you use the positive 25-degree means the rays coming from the below the optical axis. If you use the negative 25 degrees, the rays coming from the above the optical axis. And field of view is nothing but amount of the view you're going to be used for the detection of the object. And overall length of the lens to image is is less than 30 millimeters. This is the design perspective I'm telling you. And overall length means from first surface to the last image surface, what is the distance? Total complete distance is that. That will be, it should be less than 30 mm. And lens max diameter is must be less than 15 millimeter. And modulation transfer function, MTF means modulation transfer function. It should be greater than zero point 0.4 at each 20 cycles per millimeter for angle of 0 degrees and 90 degrees azimuthals. This is the requirement. And modulation is nothing but transferring the information through the carrier without changing the parameters of the signal. That's a normal terms of modulation. Here, the image value is going to be transferred to the sinusoidal carrier and reach to the image surface, and then they're going to be formed the image height, and then that should be to get the clarity of the image. It should be greater than zero point 0.4. And relative illumination, it must be greater than 60 percentage in that field of view. That means 25 degrees of field of view, the light intensity should be must be greater than the 60 percentage. These are the design specifications need to be met for our designing of compact aspheric camera using tessera lens. And for that designing process, I divided the process in three steps, 13 steps actually, and three different parts. First part is that basic designing process. Second part, advanced designing process. Third part, more advanced designing process. In basic designing process, we're going to use the specifications, whatever the I explained to the previous slide. That's a f number, effective focal length, FOV, overall length, lens max diameter, MTF, and relative illumination. All these parameters are going to be entered in the specification builder. And then we're going to select the type of the lens. There are so many type of lens. We're going to use the tessera lens which meets these specifications. Among that, we're going to select that. And finally, we're going to examine the initial performance by analysis tools. These analysis tools are so many types are there. In this webinar session, we're going to focus on three analysis tools. First one is that ray aberration tool. Second, spot diagram. Third, MTF. Aberration is nothing but depleting the image quality by means of any action. Ray aberration is nothing but it shows that how much the depleting in the image quality because of the geometrical properties of the lens. That's we're going to calculate. Spot diagram is nothing but when the rays are passed through the lens, that hit that's need to be hit on the surface. That's nothing but image surface. That hitting surface is nothing but converging. These rays are need to be how many rays are going to be converged on the image surface. That's determined by the spot diagram. And MTF determines that how much image transformation going to be happen to the image surface. That determines the MTF. Next part is that advanced designing process. It involves that two types of that. First, optimization and automatic design. Code 5 is specialization that it is specialized to provide the optimization of any design, and it depends upon the parameters you're going to use. In automatic design, it provides that different versions of the uh, different versions of the designs which gives the best result. That means that error value need to be progressively reduced. Should be it going to be done. That's going to be observed while doing the practical session on it. Third one is more advanced designing process. It involves two steps. First one is Aspire expert. Second one is glass expert. And what is the use of Aspire? What is the use of glass expert analysis? We're going to discuss further. And finally, final system performance analysis. Then we're going to see that whether the specifications all are met or not. First basic designing process. In that, completely total designing process is of 13 steps. First step is that first enter the required specification in specification builder. That means it need to be enter the system parameters, mechanical parameters, and performance parameters like EFL, FOV, F number, OEL, surface diameter, FNTF, and relative illumination. All these parameters you're going to be entered in specification builder. Then we're going to save that specifications. That specification we're going to be checked for each stage, how the performance is going to be met for each design. Step 2, select the type of patent lens to meet the above specification. There are so many patent lenses out there. Then after entering all these details, we're going to get the a few combination of lens. We're going to select the one type of combination lens which gives the best performance, and then we're going to scale that lens And then after that we're going to apply the fields, and then we can see the vignetting. Vignetting is nothing but it's like a aperture type only. Aperture is nothing but blocking the rays, but vignetting is that whatever the blocked rays are there, remaining rays which are passed through the lens, it need to be converged on the surface of image. That will be done by the vignetting. For each every step before evaluation we need to set the vignetting. That's the main important top point. Note is that before vignetting, we should select that y semi aperture of all surfaces has to be as circular apertures. Otherwise, our results will be in depleting mode. You won't get the best result. Except that object and image surface, all surfaces need to be select as circular apertures only. And then step 3, examining the initial performance of the system. That's I told you that in the initial performance of the system, we're going to use the three types of analysis tools. That one, ray aberration curve analysis, spot diagram, MTF analysis. These three things only we're going to consider for throughout the design. And step 4, evaluate the lens performance against the specification. After analyzing the performance of the system, we need to evaluate the specification and go for the specification builder, click the specification evaluator. Then in that, which are red highlighted values are there in table, that means those specification not yet met. That means it needs the design to be improved. That improvement going to be done by next step. That will be advanced designing process. In that, first we need to do optimization. Codeway is specialized for to provide the optimization in the lens to improve the performance and also meeting the constraints in the design. The constraints is nothing but what the parameters we had used in specification builder. For that, first we need to set up the variables for the optimization. In this process, we're going to use all the variables as all the constraints as the variables. And lens parameters like thickness, curvature, glass, everything is going to be changed automatically. That's why in the lens data manager, we can see that V is going to appears on all parameters. V is nothing but variable. Noting point is that being careful to have the paraxial image solve. That means the surface which is represents the image as it is, that one you should not use the word use the variable at all. It should be constant. And before optimization, we need to remove that circular apertures and set vignetting again. For each and every designing process, you need to remove the circular apertures and then set the vignetting. Vignetting is nothing but all the rays are need to be converged on the image surface. If you won't do the vignetting, the rays are not, it won't be converged on the image surface. Next step, automatic design. A code 5 is that within this fraction of time, you're going to get the various versions of designs because of optimization, because all the parameters we use that one as variable. Then it involves that setting constraints and then optimizing the design. Here, first error function. Error function is nothing but it is metric used to determine how well the lens meet the selected performance of the system. With default, we're going to use the transverse ray aberration, which minimizes the ray aberration at the image plane. Aberration is nothing but depleting the image quality by the action of anything. That may be the spherical, that may be the geometrical properties, or maybe the wave properties, whatever it may be. If it is depleting the image quality, that's known as aberration. And then to minimize that ray aberration, we're going to use the transverse ray aberration function type as default error function. And then it's going to be have the general constraints and then specific constraints also. In general constraints, we're going to use the minimum element edge thickness, minimum air center thickness, element center thickness. It's a minimum version and maximum version also. And then minimum air edge thickness. These values will be, it will be in the millimeters only. Element edge thickness is going to use the 0.1 millimeter. Air center thickness also is going to be use a 0.1 millimeter. And element center thickness minimum it should be 1 millimeter and maximum it should be 5 millimeter. And minimum edge thickness is need to be 0.1 millimeter. These are the specifications I use it for my design. That's why I'm telling. Next, after that, specific constraints. That means effective focal length of the complete design and then overall length of the complete design we're going to use. And for this design, I have used the effective focal length is 25 millimeter and OL is will be 30 millimeter. It should be less than that. As the to meet the specification what we had given in the specification builder. And then for each in automatic design, you're going to get the so many series of design steps. You're going to get it at each cycle. If you want to draw the system, then going to click the output exit controls tab, and then after we're going to save the automatic design settings, because these settings are very important while you are doing the expert analysis. Then after click OK automatic design window, then optimization process rapidly. You're going to get the different versions of the drawing of lens. In that, we can notice that element thickness, airspace, and curvature of the all going to be varied for each design. And we can examine that progress of error function value also, which is going to be reduced at the bottom of each drawing. Here in automatic design for my specifications, I got the 9 designs. Among that, it is changing the value from 2400 error value to minimum of 240. That for 240, I'm going to take it as the best design. With that, I'm going to use the expert analysis. After that, after doing the optimization, we need to see the performance of the spherical lens. That means we need to see the that aberration, ray aberration, how the performance of ray aberration will be, and spot diagram will be, and MTF diffraction will be. We're going to check it out, and then evaluation going to be done. Even after the optimization, also some of the parameters we won't get at meet that one. That's why we're going to go for the more advanced designing process. That is modernizing the design with Aspire Expert. Aspire surface are used for the to correct the spherical aberration. Spherical aberration is nothing but when the white ray is the consist of multiple colors. When it is passing through the lens, different colors have the different speeds while you traveling through the lens. Then it is going to be converged before. That means blue ray is going to be converged before the converging point. That means before the focus, and green ray is going to be converged exactly at a focus point, and red ray is going to be converged after the focus point. That's known as spherical aberration. That to remove that one spherical aberration, we're going to use the aspherical surfaces, but we can't minimize completely. But there will be trade-off between that. We're going to get the best performance with that. And to reduce the number of elements in more complicated system, that right now we are using the only 4 element system. That means 8 surfaces only. When you had taken the 40 megapixel camera, there will be surfaces of nearly 64. That many number of elements, we can't define that which surface is not good. We can't say it. That time we're going to use the Aspire Expert. And then to balance the other aberrations like chromatic aberration, astigmatism, and the remaining aberrations, if you want to remove that, that time aspherical surface are going to be used. And it provides a high performance, and it will be cost effectiveness. And this Aspire Expert, it will gives the improvement of in design. To determine first we need to Aspire Expert provide that we have the design system is that 4 element system. We're going to use it. In that 8 surfaces are there. Among 8 surfaces, which surfaces need to be converted into Aspire surface, that going to be done by the Aspire Expert. For that, it requires the input optimization sequence. That sequential file will be having the .seq text file. It consists of all the commands used in sequence to achieve your design goals. And that sequence file, I'm going to change that in 4 element system. That means 8 surfaces. I'm going to design that. I want only 2 aspires. That's why NAS I'm entering as 2. That means number of aspires are 2 only. And then number of cubic terms are 3. And the number of surfaces, it want to be checked that from first surface to the 4th surface only. That means first half of the part only I would like to check it. That's only a constraint only. There is no rule at all. But for my design, I had done like that way. And I don't put any limit on the slope, and I won't put any limit on the convex lens radius. That minimum and maximum limit also I didn't put it, and concave lens radius also I didn't put it in it all. I consider for anything whatever the value may be, I need to meet the specifications. Whatever I had given in the specification builder, it should be met it. That's it only. And diameter of the lens, it should be in vary from 8 to 240 meter for the aspherical lens only. And then after these steps, if you enter these values in command prompt of the Aspire Expert, then after that run the Aspire Expert. Then it shows that our output summary table that and determines that which surface are best to use. Then for this one, I got that S1 and S4. That means first and third surface as the best surface to convert that one into aspheric surfaces. And then those surfaces changes to QBF aspheres, and this system is going to be re-optimized again. Then after the optimization, we're going to get this type of files. That is, AE means aspheric expert, the inputs dot in. That means it consists of all the list of inputs used to run the Aspire expert. And then we're going to name that constraint sequence, and then in that constraint sequence, that is very useful for if you want to do the glass expert analysis, that we can see it in next slide. And then here I said that I have used for the design two aspires. That's why I'm going to get the two types of lens files. That is A result1.len, A result2.len. 1.len determines that result of the optimization with one aspire, and A result2.len that result of the optimization with two aspires. That performance also going to be analyzed for that. Now step 10. After the addition of aspect surface, then we're going to see the system performance. That means for everything after doing all the things, we need to do reset the vignetting, save the lens, and then execute the plots. That is ray aberration tools, spot diagram analysis, MTF analysis, and then finally evaluate the specifications in specification builder. Then even though we had done the aspheric surfaces, some of the specification we don't meet at all. For that we need of some furthermore improvement in design. That is nothing but finalizing the design using the glass expert analysis. In glass expert analysis, that it will be two steps only. First step is that first we need to enter the raw materials for the fixtures glasses, and then after do the glass expert analysis. In glass expert analysis, we're going to substitute the better materials to optimize the design. In first step is nothing but using the raw materials for that means real materials for fixtures glass. In that design, we're going to use that Scott type glass only in the basic version of glass, and then we're going to enter accept all default values like fitting and power upon glasses and replacement, everything are in default manner only we're going to use it. Then after that in LDM is nothing but lens data manager. We're going to see that in glass column all are in Scott version only. Now second step is that glass expert. After substitution of fixtures glasses, then we're going to use the best glass, because so many types are there. In Scott itself, it having the nearly 264 different type of glasses are there. Among them, which one is the best, we don't know. For that, we're going to go for the glass expert command window. We're going to answer all these questions. First, enter the list of surfaces for the glass substitution. In this design, we have the 4 surfaces, and we're going to use those surfaces names only, and then enter to accept the default behavior for handling the vignetting, because vignetting is a primary parameter that to converge the rays on the image surface. That's why we're going to handle that one as a default behavior. And then set the glass availability filtering, because I told you that we have the 268 glasses are there. Among them, which one is the best one, we don't know. That we're going to be done by the code file. And filter out the discontinued glasses, and then accept that maximum price factor for glass materials also, and then enter the keep materials without information, because this design is just a normal only, no? It's a basic version only. That's no need to keep the information at all. If you have the perfect design, then we need to keep the information about the materials also. And then accept the default boundaries on refractive index, and set to the default strain resistance factor, and set the target transmission for the system, and enter the maximum different thermal expansion for the cemented elements. Cemented elements is nothing but we can see that in achromatic doublet, the convex and concave lens are going to be combined together. There is no air gap between them. Those elements are known as cemented elements. And in this design, I'm going to use the 2 achromatic doublets. That's on front side and the back side also. And then different thermal expansion, because there is no air gap in between them. When you're going to keep it in the different type of environments, that means cold environments or maybe the hot environments, that gap is going to be created or maybe be reduced. That is also cause that will also cause that depletion in the performance of the system. And then this is a very important factor, that if you want to work in the underwater, and then if you want to work in the different type of environments like hot environments and even cold environments, this thing is a very very important. And then after the glass expert analysis, finally we're going to do final system performance analysis. That means we're going to check that quick ray aberration plot with the first basic painted one lens to the glass expert lens version, and we will see that which one gives the best performance. And then quick spot diagram also, MTF also. After that, finally we're going to evaluate the specification in specification builder. In that specification builder, whatever the tester lens specifications we had given, whether those specifications are met or not, we're going to check it out. Then if it is met, we're going to save that lens, and that is the best design, we're going to get it. This is the process we're going to do it in for any design in code 5. This is the basic process. And then after the processing that, the work done for these 2 months, that is I'm going to discuss in result and discussions. First, I had taken the patent lens of Japan patent lens, which consists of 4 elements. That's we can see 1, 2, 3, 4. This is the achromatic doublet. One achromatic doublet is consist of that. And then I'm going to conclude the presentation like this way. First, what we had done is we had done the analysis and the basic design, and later we performed the optimization. After that, we proceed to Aspire expert analysis. After that, if the specifications also doesn't mean that, finally we complete the design with glass expert analysis. At the end, we compare all the initial results with optimization, Aspire expert, and glass expert results. Then after the glass expert analysis, system is provided that its performance improved drastically and met all the targeted specifications except that overall length. We need to compromise on that one, because all the constraints we can't meet at all. We need to compromise with the having the trade-off between the parameters. That's very important. And my future scope is that it involves that right now in complete from the October to February, whatever the work I had done is that basic understanding of optical imaging fundamentals, and then after basic understanding of code 5, and then and basic use of code 5, how to use it for the designing process. That's we had understood. And then coming a few months, I'm going to give the webinar on that. First, what is the meaning of micro lens array, and then we need to design that one in basic version, then apply all the analysis tools whatever I had used earlier, then apply the optimization, apply the Aspire expert analysis, then after apply the glass expert analysis. And I would like to check that one which parameter is enough. That means if you satisfy the requirements with the Aspire, we can stop that design there on itself. Otherwise we can proceed to glass expert also, and then evaluate the system performance. These are the things I'm going to do in future. And then these are the books I referred for the theoretical analysis.